Hi, we'll be discussing about onshore wind power as an alternative to fossil fuels, and I'll be briefly introducing the onshore wind power. This study from 2015 has quantified the increase in world population since past few years, and they also quantified the increase in energy demand with this increase in world population, and which is as expected that if the population is increasing, there'll be an increased demand of energy as well. So basically, there's a requirement for meeting this increase in energy demand, and how do we meet this demand? We might say that there are fossil fuels that can be used to meet this energy demand. However, fossil fuels burning releases a lot of carbon dioxide into the atmosphere, and there have been a lot of studies that have shown that. And the carbon dioxide emissions from fossil fuel burning have been on the rise, as seen in this study as well. And there has been it has been established that there's a correlation between carbon dioxide concentration in the atmosphere and a temperature rise, which is the major cause for global warming. And there have also been quantification studies for the fossil fuel reserves, and it has been seen that the fossil fuel reserves are supposedly going to come to an end. So this raises a need for an alternative source, and there are a lot of renewable energy sources, such as hydropower, solar power, as well as wind energy. And Australia has made use of most of these renewable energy types. We, in particular, will be talking about wind energy, and there are two types of wind energy farms. One is onshore wind farm, and one is offshore wind farm. They basically vary in the capacity that they can generate the energy in, and also the size of the wind turbines. In our presentation, we'll be talking about onshore wind farms in particular, and we'll discuss onshore wind farms with respect to carbon dioxide emission, land use, and its feasibility in Australia.
Comparative to the extensive land use associated with fossil fuels, the land use and environmental impact of wind energy is minimal. The mining of resources and the ecological impact of construction both contribute to the land impact of electricity generation. The mining infrastructure and open-cut mines for the extraction of coal is the major contributor to coal power land occupation. Wind turbines require far less minerals and a smaller impact zone for construction. However, wind energy production still incurs vegetation, soil and wildlife loss and an impact on local wind patterns. After construction, the land impact of wind energy occupies the support structure and a protected radius surrounding the wind turbine, allowing for dual-purpose facilities, utilizing the land surrounding wind turbines for solar farms or agricultural purposes. This allows for increased centralized energy production, or the implementation of wind farms in existing agricultural areas as a secondary source of income for farmers. When incorporating the land use of material extraction and electricity generation, the United Nations Economic Commission for Europe found wind energy required 16 times less land per megawatt hour than coal and a similar land use to natural gas. The implementation of large-scale wind farms in Australia requires finding a balance between appropriate and consistent wind speeds, proximity to electricity networks, and maximising the productivity of the land wind farms utilise. The coastlines of mainland Australia and Tasmania experience the highest mean wind speeds in the country. While most of these areas are far from large electricity networks, there are significant regions of Australia capable of producing large amounts of wind-generated electricity, particularly for the South Australian electricity grid and the development of dual-purpose wind farms in agricultural land, particularly in Victoria, which maximises the land use available for wind power.
Although there is no carbon emissions directly associated with the operation phase of renewable technologies like wind power, there remains carbon emissions associated with the production line and the life cycle of these products. In particular, the raw material extraction, as well as the manufacturing, the transportation, the installation, and the decommissioning of these power plants has carbon emissions associated with them, and that's what we're about to look at here. Our research returned two key findings. The first one is that when a review of life cycle assessments that have been carried out around the globe was performed, it returned that on average 86% of the carbon emissions associated with the given power plant came from upstream processes, this being manufacturing, installation, and construction, when we looked at specific cases, it became clear that transportation and installation were that culprit. When a study was done, as in the bottom graphic here, between onshore and offshore wind, it became clear that it was that phase that made the biggest difference between onshore and offshore, and it made clear that onshore was far less carbon intensive than offshore wind projects. When you start to think about it, it makes a lot of sense that the transportation of such large bits of machinery and their installation in rural areas is very carbon intensive. And that's even more obvious when you start to think about the process of trying to do that in the ocean. In the end, these studies tend to return figures around about 10 grams of carbon dioxide equivalent released per kilowatt hour of power generated. That is about 1/100th of a traditional coal-fired power plant, about 1/3 of a nuclear power plant, and about 1/5 of a solar power plant. So not only does wind outperform fossil fuels, but also outperforms other renewables that are being actively sought in the present day. What's important to note is that not only are we good now, but there is a bright future. Improved recycling and economies of scale that will no doubt occur in the expansion of the industry over the next 20 years should bring down the rate of carbon emissions associated with the energy production. But furthermore, the reliance on batteries to kind of operate renewable power systems does cause that carbon emission rate to be higher, and hopefully in the future better systems are established within the grid that will allow that process to be more efficient.
Australia is blessed with a vast expanse of open land and coastlines that stretches over 35,000 kilometers. These geographical features provide the perfect conditions of harness with wind energy. The country boasts some of the best wind resources in the world, particularly in regions like South Australia, Victoria, and Western Australia, making it an ideal location of the wind farms. Also, government support and incentives have played a very provisional role in the growth of wind industry in Australia. Initiatives such as Renewable Energy Target and the Clean Energy Finance Corporation have provided financial incentives and regulatory framework that encourage investment in renewable energy projects. These policies have helped reduce the cost of wind energy production and make it more attractive in investors. Over these years, there have been significant technological advancements in wind turbine design and efficiency. Turbine blades have become larger and more aerodynamic, allowing the greater energy capture from the wind. Additionally, improvements in general design, generative technology, and control system have increased the reliability and performance of wind turbines. As technology has provided the economic of scale have come into the play, the cost of producing wind energy have decreased significantly. As we can see from the chart on the right, due to the technological advance in recent years, the cost of wind energy for moderate wind have been reduced from 7 cents per kilowatt per hour to 4, far exceeding and ahead of Department of Energy's goal, which shows that the development of onshore wind is moving away from fossil fuels and heading in a very good direction.
Okay, so before we conclude this presentation, we need to consider some key limitations. Let's just have a look at 2. So as we've been talking about onshore wind, we need to think firstly, well, where are we going to put them? And so this equates to land. So what's the land use scale that's required? And in particular, with the horizontal axis wind turbines we've been looking at, these have large rotor diameters and need a large amount of space. Additionally, with these, they also need to be placed in the wind flow direction in order to operate efficiently. So what can we do? Firstly, we could integrate onshore wind turbines with crop agriculture. So one key benefit of this is that it would help reduce further habitat destruction and biodiversity loss. But in particular, in the face of climate change, and especially in the south of Australia, where climate change models have reported increased temperatures and decreased rainfall, wind turbines can help support crop production in a couple of ways. So one, through creating the extra wind turbulence, this helps keep crops cooler. And secondly, they can also extract moisture from the air for potable water collection. So the second thing we can do to address the wind flow direction limitation of the horizontal axis wind turbines is to perhaps combine them with vertical axis wind turbines. So current research states that the horizontal axis wind turbines are more efficient in producing electricity than the vertical axis wind turbines. However, they operate at different wind speeds and wind directions. So looking at the horizontal, they typically operate from a wind speed of 11 kilometers per hour, whereas the vertical axis wind turbine operates at speeds of less than 5 kilometers per hour and also in 360 degree around. So based on that, it might be worth having a combination of the two of them at the same place. Thank you.
This is a list of the references that were used for the presentation.